Hello students, welcome to the class of Basic Electrical Engineering. It followed by the code EE201. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. Today this is our third lecture and we will discuss on the generation of AC and the VI relationship in the RLC series circuit. In this video lecture, we will discuss on the generation of AC, the VI relationship in pure resistance, pure inductance and pure capacitance with the AC excitation with the example and references. So how the AC has been generated? Now, at present day, a large percentage of electrical energy, almost all the electrical energy being used for the domestic and commercial purpose is generated in the form of alternating current. In fact, almost the whole of the vast amount of electrical energy used throughout the world for every imaginable purpose is generated by alternating current generators. This is not due to any superiority of alternating current over direct current in the sphere of applicability to the industrial and domestic use. In fact, there are certain type of works for which alternating current is unsuitable and therefore direct current is absolutely necessary, such as for the electroplating, the production of industrial gases, electrotyping, refining of copper, storage batteries, municipal traction, etc. But in some power applications, that AC motor is unsatisfactory for metal rolling mills, paper making machines, etc. Now the direct current required for this application is nowadays derived from an AC supply by the use of suitable converters and rectifiers. So why we generate electrical energy in form of the alternating current? Because the AC generator have no commutator and can therefore be built in very large unit to run at high speed, which produce high voltages, almost 33 kV. So the construction and operating cost per kilowatt is very much low when it is compared to the DC generators and voltage which are limitedly comparatively low values. Alternating current can be generated at comparatively high voltages and can be raised and lowered by the transformer using. But this transformer cannot be used in the DC current. The AC induction motor is much more cheaper in initial cost and maintenance also, because it has no commutator and more efficient than DC motor for a constant speed work. So it is desirable to generate power as an alternating current. The high transmission efficiency in AC makes the generation of electrical energy economical by generating it in the large quantity in single station and distributing over a large territory. The switchgear for AC system is much more simpler than it is required for the DC system, as well as the maintenance cost of an equipment is very less in case of AC. So, how to generate the AC or the alternating EMF? Now we know that an alternating EMF can be generated either by rotating a coil within a stationary magnetic field or by rotating magnetic field within a stationary coil. So the EMF generated in both the cases will have the sinusoidal waveform, and the magnitude of EMF generated in the coil depends upon the number of turns of the coil, the strength of the magnetic field, and the speed at which the coil or magnetic field rotates. So the first one is employed in case of small AC generators, and the later one is employed for the large AC generators. So now consider a rectangular coil with n number of turns rotating in the counterclockwise direction with the angular velocity of omega radian per second in the uniform magnetic field. So the time being measured for the instant of coincidence of the plane of the coil with the x-axis, and at this instant the maximum flux phi max links the coil. So if we assume that the position at the reference, then after moving it counterclockwise direction for the t seconds. Now if this rotate a complete one rotation, then it will generate a complete one sinusoidal wave. So here we are considering the n number of turns which is rotating in counterclockwise direction with the angular velocity of omega radian per second within the uniform magnetic field, and at the horizontal position after the moving in the counterclockwise direction of the t second, the angle is theta, and this theta angle through which the coil has rotated in t second is equal to omega into t. And in this position, the component of flux along perpendicular to the plane of coil, that is phi max cos omega t. Now the flux linkage of the coil at this instant becomes the number of turns of the coil into linking flux. So that means the instantaneous linking flux becomes n into phi max cos omega t. Now how much EMF should be induced? Now the induced EMF at any instant is given by small e equal to minus d dt of n into phi max cos omega t. Now if we put it, and then we will find out the EMF induced is equal to phi max into n into sine omega t. Now when the omega t is equal to 0, then sine omega t becomes 0. So the induced EMF will be 0. At omega t is equal to pi by 2, we get sine pi by 2 is equal to 1. So the induced EMF will be maximum, which we can denote by Emax. And similarly, when it goes to more 190 degree rotation, then it will be again 0, and again to the minimum value or minus of Emax, and after further rotation through an angle 2 pi radians, then it will be 0. So the sine curve will be completed when the coil rotates through an angle of 2 pi radians, and the induced EMF will have the maximum value Emax when the coil has turned through pi by 2 radian or 90 degree in the counterclockwise direction from the reference axis or the horizontal axis. So I have put here the theta values, or theta becomes 0, then 90, 180, 270 and 360. Then we can see the angle becomes 0, 90, 270, 0, 270 and then 360 degree. So each degree of rotation, after one complete rotation from 0 to 360 degree, one complete cycle of sinusoidal wave has been generated, and that is the AC waveform. Next is the VI relationship in pure resistance with AC excitation. So we know when a pure resistance is connected in the DC supply, then DC current is flowing through it. Now the AC supply has been connected to it. So when the AC supply is connected to a resistance, then the current is flowing through the resistance become the sinusoidal one. So we know the voltage is expressed by the equation V max sin omega t, as it is a sinusoidal wave. So the current will be represented by V max divided by R into sin omega t, which is nothing but I max sin omega t. So we can see that both the current and voltage are in the same phase, because both has been starting from 0 and both has been completed by 2 pi. So pure resistive or a non-inductive circuit is a circuit where the inductance is so small at the normal frequency its reactance is negligible when it is compared to resistance. So what are the examples of pure resistive circuits? Those are the ordinary filament lamp, water resistances, etc. And these are the non-inductive resistances. And if the circuit is non-inductive, that means no reactance EMF or self-induced or back EMF is set up, and the whole applied voltage is utilized in overcoming the ohmic resistance of the circuit. And the total current or ohmic drop, that is, if it is I into R, then the total current is Vmax divided by R into sine omega t. So next is the VI relationship in pure inductance with AC excitation. So in inductive coil is a coil or without an iron core having a negligible resistance. But practically pure inductance can never be had as the inductive coil has always small resistance. However, a coil of thick copper wound on a laminated iron core has negligible resistance and it is known as a choke coil. Actually, inductors or choke coils are made of iron core because large valued flux density can be produced in iron cores. So inductances of large values can be had. Air core inductors become too much bulky to have an inductance of a given value. Now, when an alternating voltage is applied to a pure inductive coil, an EMF, which is known as the self-induced EMF, is induced in the coil and it opposes the applied voltage. Since the coil has no resistance, at every instant, applied voltage has to overcome this self-induced EMF only. Now, if the applied voltage is Vmax sine omega t, then the self-inductance of the coil is L Henry. Then we can write EL is equal to minus of L di dt. Now the applied voltage at every instant is equal and it is opposite to the self-induced EMF. So V is equal to minus of EL, or we can find out the equation of I, which is I max sine omega t minus pi by 2. Because Vmax is equal to minus L di dt, or di dt is equal to Vmax by L into sine omega t, or from here we can find out I is equal to I max sine omega t minus pi by 2. Now what this minus pi by 2 indicates? That means if we consider the voltage signal, it has been started from 0, then because omega t is equal to 0, then I will be lagging behind the voltage by a 90 degree. So from this expression we can say that the current flowing through a pure inductive coil, it lags behind the voltage by the angle pi by 2 or 90 degree. So next is power in the pure inductive circuit. So instantaneous power is given as V into I. V means V max sine omega t and I is the I max sine omega t minus pi by 2. So the power measured by the wattmeter is the average value of P, which is 0, since average of sinusoidal quantity of double frequency over a complete cycle is 0. Hence a pure inductive circuit, the power absorbed is 0. So during the second half of the cycle, the current and the magnetic flux of the coil increases and the coil draws power from the supply source to build up the magnetic field. That is, the power is drawn positive and the energy drawn by the coil from the supply source is represented by the area between the curve P and the time axis. And this energy stored in the magnetic field during this build up is given as 1 by 2 into L into I square max. And the next half cycle, the current decreases and the EMF of the self-induction will however tend to oppose this decrease. Now the coil acts as the generator of electrical energy and returning the stored energy in a magnetic field to the supply source. And now the power drawn by the coil is negative and the curve P lies below the time axis. And the chain of events repeats itself during the next half cycles. So a proportion of power is continuously exchanged between the field and the inductive circuit, and power consumed by the pure inductive coil is zero. And in practical sense, the reactance of an inductor dissipates a net energy of zero, which is unlike the resistance of the resistor, which dissipates energy in form of the heat. Next is the PI relationship in pure capacitance with the AC excitation. Now the inductor has been replaced by a capacitor, and what is happening during this capacitor? So voltage is impressed across the plate of the perfect capacitor when it is connected to DC, and it will become charged to full voltage almost instantaneously. Now the charging current will flow only during the period of build-up, and it will flow as soon as the capacitor has attained the steady voltage of the source. It implies that for a direct current, a capacitor is a break in the circuit or infinitely high resistance. Now a sinusoidal voltage has been applied to a capacitor, and during the first quarter cycle the applied voltage increases to the peak value and the capacitor is charged to that value. The current is maximum in the beginning of the cycle and becomes zero at maximum value of the applied voltage. So there is a phase difference of 90 degrees between the applied voltage and the current. During this first quarter cycle, the circuit current flows the normal direction through the circuit and the current is positive. In the second quarter cycle, the voltage applied across the capacitor falls, the capacitor loses its charge and current flows through it against the applied voltage because the capacitor discharges into the circuit. So the current is negative during the second quarter cycle and it attains a maximum value when the applied voltage is zero. Similarly, for the third and fourth quarter cycles, repeat the events of first and second with the difference that the polarity of the applied voltage is reversed and their corresponding current changes. Or alternating current flows in the circuit because of the charging and discharging of the capacitor. So here V is equal to V max sin omega t and I is equal to ddt of Cv, where I is also ddt of Q. So we can find out I max is equal to sin omega t plus pi by 2. Due to this plus pi by 2, the current leads the voltage by 90 degrees. So the power in the pure capacitive circuit can be obtained by multiplying the voltage and current. So V into I, which gives us V max sin omega t into I max sin omega t pi plus pi by 2, or the average power can be found out by V max I max by 2 into average of 2 sin omega t over a complete cycle, which is equal to 0. Similarly, the power absorbed in a pure capacitive circuit is 0, and we can show it through this graph also. And the energy taken from the supply, the circuit is stored in the capacitor during the first quarter cycle and returned during the next. So the energy stored by the capacitor at maximum voltage across its plates is obtained as half of Cv square. And this can be realized when it is recalled that no heat is produced, no work is done while current is flowing through a capacitor. As a matter of fact, in commercial capacitors, there is a slight energy loss in the dielectric in addition to a I square R loss due to flow of the current over the plates having definite ohmic resistance. So next is the inductive reactance. So inductive reactance is defined as the opposition offered to the flow of AC by a perfect inductor. And the unit of this inductive reactance is ohm and symbol is XL. The inductive reactance value of an inductor at a particular frequency can be found out by the equation XL is equal to omega L or 2 pi Fl. Now E is equal to minus L di dt or E is equal to minus V. So we can write V is equal to L di dt. I is equal to I max sin omega t. So V can be written as L dt of I max sin omega t. So from here we can write V is equal to omega into L into Im into cos omega t. And at t is equal to 0, we can find out cos omega t is equal to 1 and V is equal to V maximum. So we can write the inductive reactance XL is equal to omega L, or it is equal to 2 pi Fl, where L is the inductance, F is the frequency of the given system. Next is capacitive reactance. The capacitive reactance happens when the opposition offered to the AC current due to the potential difference developed between the capacitor plates, and it is more convenient to refer this opposition in terms of a quantity measured in ohms, and this is known as the capacitive reactance denoted by XC. So we know that Q is equal to C into V and I is equal to dQ dt. So I becomes C into dV dt, where V is equal to V max sin omega t. So if we put the values, then we can find out I is equal to omega C into Vm cos omega t. And at t is equal to 0, I becomes I maximum and cos omega t becomes 1. So we can write I max is equal to omega C into Vm, or this Xc can be written as 1 divided by this omega C, or 1 divided by 2 pi fc, where f denotes the frequency and c represents the capacitance of the given system. So let us take one example. Here we need to calculate the power dissipated by a resistance when it is connected to a supply voltage equal to 35 sin 3140. So now the RMS value of voltage we can find out by the formula. It becomes 0.707 into Vm, or P is equal to V square divided by R. So P becomes 1.09 watt. And next example is a current of 250 milliampere flows through a perfect inductor and it is connected to a 5 volt 1 kilohertz supply. We need to find out the inductance value. So we know XL is equal to V divided by I, and V is given as 5 and I is given as 0.25 ampere or 250 milliampere. So XL can be calculated as 20 ohm. And we know the value of XL becomes 2 pi FL. So if we put the values of frequency and XL, then we can find out the value of L, that is equal to 3.18 millihenry. Now a 0.47 microfarad capacitor is connected to a variable frequency. It provides the output voltage of 25 volt. We need to find out the current flowing through the circuit for 200 Hz and 4 Hz frequency. So first we will find out the XCs, and XC is equal to 1 by 2 pi fc. We know the value of F and C over here, and so we can find out the value of XC. And once we can find out the XC, then we can find out the I, which is nothing but the ratio of voltage and the capacitive reactance. And it becomes the result, the current is 14.77 milliampere, and we can follow the same steps by changing the frequency here, because for the second one the frequency is 4 kilohertz, and then we can calculate the second current becomes 295.3 milliampere. So in this way, using the formula, we can find out the current flowing through the circuit when the frequency is differs from second. These are my references. So I hope after this video lecture you have a clear idea about today's topic. So now we will go through some question answer session in context of this video lecture. You are requested to go through it gradually. Answers of these questions has been attached at end of each question.